Hi folks, welcome back. We are starting section 3.4, which is determinants, and let's go. Let's see how this does. So we're going to start with a 2 by 2 matrix, like A, B, C, D here. And the determinant, which we saw right at the end of the last video, is the value A times D. So we're going to multiply this diagonal together, minus B times C. We multiply this diagonal and we measure the difference between them. So for an example, if my matrix was 2, 6, 1, 5, 2 times 5 is 10, 6 times 1 is 6, 10 minus 6 is 4, and so the determinant is 4. In a little while, we'll talk about what that 4 means and how to interpret that, but let's go ahead and move on. So calculate the determinant of this matrix. That would be 3 times 6 minus 4 times 5, which is 18 minus 20, which is negative 2. Okay. Here's the geometric interpretation of the determinant. Suppose that we had a region S in the plane, a closed region S, and a linear transformation whose standard matrix is A. Then the area of the transformed version of S is the area of S multiplied by whatever the absolute value of the determinant of A is. Now, sometimes the determinant is negative and area can't be negative, so we have to strip off the negative sign here. But the area is the magnitude of the determinant, the absolute value of the determinant times the area. That is, except for the negative sign, for possibly the negative sign. The determinant is the magnification or the reduction factor of its linear transformation. That is, so when the determinant is 4, it means it makes shapes 4 times bigger. When the determinant is negative 2, even though that's negative, it doesn't make the shapes smaller, it makes them bigger by a factor of 2. 1/2 would make a determinant smaller because it would make it by a factor of 1/2. All right, let's move on. Let S be the unit circle and let A be the matrix 3, 0, 0, 2. If T is the linear transformation whose standard matrix is A, describe the transformed version of S and find its area. All right, so let's sketch this out. S is the unit circle. And so that's going to be roughly like so. And so let's talk about what happens to the transformed version of S. Well, the standard vectors E1 and E2 are just 2 radii of S. That is, E1, let me change colors here. E1 is this radius and E2 is this radius. And the transformed version of E1 and the transformed version of E2 change size. The transformed version of E1 is now 3 units long, it's 3, 0. And the transformed version of 2 is now 2 units long, it's 0, 2. So this is the transformed version of E1 and the transformed version of E2. And so this circle has been stretched, but it's been stretched unevenly. It's been stretched more in the horizontal direction than the vertical direction. And so instead of having a circle, we now have an ellipse. And we know the formula for a circle, formula for a circle is pi r squared. The formula for an ellipse, some of you may have seen it, some of you may not have. But what we know here is that the determinant of A is 6 minus 0, which is 6. And that means the ellipse is 6 times bigger than the circle. And so the circle has an area of pi r squared, and since it's a unit circle, the radius is 1. So the area of the circle is pi. The area of the ellipse, we know for a fact, has to be 6 pi. Even if we don't know a formula for the area of an ellipse, we know that this transformation enlarges the area by a factor of 6. And so the area of the ellipse is 6 pi. All right. So let's find the area of this ellipse. So now my E1 and E2 have not just been stretched, they've been rotated a little bit. The coordinates for the transformed version of E1 are 2, 2. And the transformed version of E2 is -1, +1. And so our matrix is 2, 2, -1, +1. The determinant of that matrix is 2 minus a -2, which is 4. And so this ellipse is 4 times bigger than a unit circle. And we already know that the area of the unit circle is pi, and so the area of this ellipse is 4 pi. Let's keep going. We can do this for triangles also. We know a formula for a triangle. The area is 1/2 base times height. And over here, that's pretty easy. This is the base. This is the height. And so the area is 1/2 times 1 times 1, or 1/2. But over here, this is the base, and this is the height. And that, the base we could probably figure out using the Pythagorean theorem. It's 2 units over and 1 unit up, square root of 5. The height, we don't know what this point is, and so we can't figure out what this distance is very easily. This is going to be very hard to find out using base times height. But using a linear transformation, my base and my height are E1 and E2. If we transform this so that this is the transformed version of E1, and this is the transformed version of E2, then this is the vector 2, 1, and this is the vector -1, 3. The matrix is 2, 1, -1, 3. The determinant of that matrix is 6 minus a -1, which is 7. And so this triangle is 7 times bigger. And since this triangle is 7 times bigger, then it must have an area of 7 halves. I think we'll do one more. Let's find the area of this parallelogram. So a 4-sided figure using E1 and E2, we'll start with just the unit square, E1 and E2. All right, and the area of that unit square is 1. Now we're going to transform and E2 into the sides of this parallelogram. And this side, be careful because it doesn't start at the origin, so it's not 3, 2, it's just 2 units over and 1 unit up. That vector is 2, 1, and this vector is 1, 3. And so if we look at the determinant of 2, 1 in the first column and 1, 3 in the second column, 6 minus 1 is 5. Then the parallelogram is 5 times bigger. And so its area is 5. So determinants give us a nice way of calculating areas of shapes that are linear transformations of easier versions of shapes. If I know how to find the area of a triangle, then I can use this to find the area of any triangle, even if it's not, doesn't have the base or the height parallel to the x and y axis. If I know how to find the area of a circle, I can use it to find the area of an ellipse. If I know the area of a square, I can find the area of a parallelogram. So this, expands our geometry repertoire considerably. We're also going to be able to do some algebraic things with it. Let's move on. In order to do some algebra with this, we would like to go beyond just 2 dimensions, though. We would like to be able to calculate the determinant of a larger matrix. And so we're going to cover some definitions. One is, there are 2 definitions. One of them's on this slide, and then one of them's going to be in a couple of slides. A submatrix. If A is a square matrix, then a submatrix is found by removing 1 row and 1 column from A. And we use the little subscripts to indicate which row and column we have removed. So all we're doing is we're reducing the size of the matrix by clearing out a row and a column. So if this is the matrix A, and I want to find the submatrix A3, 4, that means we're going to remove row 3. So that row goes away. And column 4. And so this column goes away. The numbers indicate which row and which column. And now we're, instead of having a 4 by 4 matrix, we just have this 3 by 3 matrix. 1, 3, 0. 2, 1, negative 2, 7, negative 2, 9. All right. That's what a submatrix is. Cofactor. If A is a square matrix, then a cofactor of A is found by calculating the determinant of the submatrix and then multiplying that determinant by either a 1 or a negative 1 according to this rule. If the subscripts add up to an even number, then we multiply the determinant by 1, which doesn't have any change. But if the subscripts add up to an odd number, then we flip the sign and multiply this by negative 1. And we use a capital C to indicate a cofactor. So on the next slide, we're going to do an example. But remember, if the subscripts are even, we don't change it. If the signs or subscripts add up to an odd number, we change the sign. We multiply by negative 1. So in this example, we have this matrix A, and we want to find the cofactor in the 2, 3 position. So that means we are eliminating row 2, and we're eliminating column 3. And so that would leave you with 1, 3 on top and 3, 5 on the bottom. But 2 plus 3 is odd. And so we're going to change the sign. And so this determinant is 5 minus 9, which is negative 4. But by changing the sign, our final answer is positive 4 instead. So that's an example of a cofactor. We can calculate the determinant of a 3 by 3 matrix using a technique called cofactor expansion. To find the determinant of a 3 by 3 matrix, we're going to choose any row or any column of A. It doesn't matter which row or column we pick, but we're going to multiply every entry in that row or column by its cofactor, by the cofactor corresponding to that entry's position. And then we're going to add up the products we found. So we're looking at a 3 by 3 matrix. I might pick this row here, and the entries might be, say, A, B, C. I will calculate A times the cofactor in this position, which is row 2 and column 1, and then B times the cofactor in this position, which is row 2 and column 2, and then C times the cofactor in this position, which is row 2 and column 3. And that would be the determinant if I chose the middle row, but I can choose any row or any column that I want. All right, so let's try an example. We're going to use cofactor expansion to compute the determinant of this matrix here. So first of all, we pick a row or a column. So I like the number 0 because I know how to multiply by 0. And so I would like to use that 0 to make my life a little bit easier. So I'm going to pick the top row. And now I know that the determinant of A is 1 times the cofactor in the top position plus 3 times the cofactor in the next position, which is row 1, column 2, plus 0 times the cofactor in the third position, which is row 1, column 3. All right. So the cofactor in the 1, 1 position is the determinant. If I eliminate row 1 and column 1, the entries that I'm left with are 2, -1, 4, 1. And then I have 3 times the cofactor in the 1, 2 position. And if I eliminate row 1 and column 2, that leaves me with 2, -1, 1, 1. But 1, 2 is odd, so we have to change the sign. So I'm going to make this turn negative. Because 1, 2 is an odd position. All right, what does that add up to? That's going to be 2 minus a -4 is 6, minus 3 times 2 minus a -1 is 3, and 6 minus 9 is -3. And so that's the cofactor that we get. All right. Okay, let's move on. Just as a bit of notation, the determinative matrix is sometimes written with vertical bars, so it looks like an absolute value around an entire matrix. So we could, instead of writing the determinant of A, we could write the vertical bars around the matrix, and it means the same thing. In both cases, the answer is -3. All right. Let's try this matrix. And we're going to try this twice. We're going to do 2 different cofactor expansions. Because I want to at least give you some evidence for why it doesn't matter which row or which column we pick. That the geometry of the transformation is the same no matter which direction you approach the geometry from. It's still the same transformation. So again, I like zeros, so first time I'm going to try the bottom row. And now I get that the determinant of A is -1 times the cofactor in the 3, 1 position plus 0 times the cofactor in the 3, 2 position, plus 0 times the cofactor in the 3, 3 position, and 0 times anything I don't care about. This is the only one I'm really interested in. In the 3, 1 position, we're left with negative 1, 0, 3, negative 2. And that's 2 minus 0. And so we get negative 1 times 2 is negative 2. This column also has 2 zeros in it. So we could use the column, and we get the determinant of A is 0 times the cofactor in the 1, 3 position, minus 2 times the cofactor in the 2, 3 position, and plus 0 times the cofactor in the 3, 3 position. So that's negative 2 times the determinant in the 2, 3 position. When we leave out row 2 and column 3, we're left with 2, negative 1, negative 1, 0. And 2 plus 3 adds up to an odd number. And so we're going to change the sign and make this positive. Sign change, because 2 plus 3 is odd. And that leaves us with 2 times 0 minus 1 is negative 1, and 2 times negative 1 is negative 2, and we get the same answer regardless of which geometric direction we are approaching the transformation from. We can do it from the horizontal, or from the vertical, from the x direction, the y direction, the z direction. It doesn't matter. We always get the same determinant. All right. So let's move on. If a square matrix is an echelon form, then we have a shortcut for finding its determinant. And let's see that. So let's calculate the determinant of this matrix. Now this matrix is an echelon form. Which means the bottom row looks really nice because of all those zeros there. And so the determinant of A is 0 times the cofactor in the 3, 1 position, plus 0 times the cofactor in the 3, 2 position, plus 5 times the cofactor in the 3, 3 position. And that's the only one I care about. But the cofactor in the 3, 3 position is the determinant of 3, 19, 0, 2, which is 5 times 3 times 2 minus 19 times 0. Well, because of this 0 here, which is also part of echelon form, this diagonal doesn't make any difference, and this diagonal does. So this is just 5 times 3 times 2, but it's just in this number. Let me see if I can. That's not good. Let me go back there. 5 times 3 times 2. Those are just the numbers that are on the diagonal. That in the bottom row, these zeros meant the other cofactors didn't matter. And this 0 meant that the 19 doesn't matter because of it just gets multiplied by 0. And so the only numbers that matter are the 3 numbers that are on the diagonal. And that's a useful trick, because if we get to larger and larger and larger matrices, then if the matrix is in echelon form, we can compute the determinant really easily. The determinant of this matrix is 3 times negative 2 times 2 times 5 times negative 3, which is negative 6 times 10 is negative 60. Negative 60 times 3 is 180. And we're done. So if the matrix is an echelon form, all we have to do is multiply down the diagonal. If the matrix is not in echelon form, we can row reduce. It is possible to use row reduction to convert a matrix to echelon form. But there's a price to pay. Row reduction changes the determinant of a matrix. And so we have to keep track of those changes that we've made as we go. So let's talk about how row reduction changes determinants. First of all, if we switch two rows of a matrix, then that changes the sign of the determinant. So as an example, if I start with 3, 5, 2, 4, that determinant is 12 minus 10, which is 2. But if I switch the order of the rows, then now I have the 10 coming first and the 12 coming second, and my sign has changed. And so if I have a matrix that's not in echelon form, but I want to put it in echelon form so that the determinant is easy, then if I switch two rows during the row reduction process, I have to remember that that changed a sign, and then I have to change the sign back when I'm done. I have to undo that change when I'm finished. If we multiply or divide a row by a constant, that changes the determinant by the same amount. So this is the matrix 4, 8, 1, 5. The determinant is 20 minus 8, which is 12. If I were to take 1/4 times row 1 to change 4, 8 into 1, 2, that's perfectly legal. But now my determinant isn't 12, it's only 3 because I made this row 4 times smaller. And so the determinant also got 4 times smaller. So scaling a row changes the determinant by that amount. And then there's one other step. Let's talk about that one. This was a little tricky, and the book describes this step a little differently, but that's okay. We'll muddle through this. Using a combination, adding a multiple of a row to another row, changes the determinant by the coefficient of the row that was changed. So here's an example. If I look at this matrix, 1, 2, 4, 7, the determinant is -1. If I calculate row 2 minus 4 row 1 to change this 4 into a 0, that's 4 minus 4 is 0, 7 minus 8 is -1. But I'm changing row 2, and the coefficient of row 2 is 1, which means that the determinant scales by a factor of 1, which is no change. And so the determinant is still the same answer that we had before. -1 minus 0 is still -1. But here's a different example down here. If we do calculate this determinant, it's 12 minus 10. And this time I'm going to try to get a 0 here by doubling row 2. 2 times row 2 minus row 1. So that makes 4 minus 4 is 0. And then 6 minus 5 is 1. But row 2 was the row that changed. And the coefficient of the row 2 is a 2. And so the determinant doubles when we do this. So it's now 4 minus 0, which is 4. The determinant got twice as big because the row that we were changing got multiplied by 2 in this linear combination. So using a linear combination is a legal step, but it changes the determinant by the coefficient of whichever row is being changed in the linear combination. So here's just a quick review. What effect do these operations have on the determinant of a matrix? You should be able to answer these questions based on what we did. If we multiply row 3 by -4, then what does that do to the determinant? It multiplies the determinant by -4 also. What happens if we compute row 3 minus 2 row 1, and we use that step to change row 3? The coefficient of row 3 is 1, and therefore there is no change. What happens if we switch row 2 and row 4? This multiplies the determinant by a factor of -1. And finally, what happens if we compute this combination, but we're using to change row 1? Well, the coefficient of row 1 is a -1, and so this causes the determinant to change by a factor of -1. All right. Okay, so let's put this together and try an example. We have a matrix here that is not quite in echelon form, but we do see some nice zeros. And we would like to compute the determinant of this matrix. Okay? All right. So what I'm going to do is I'm going to just start with a blank page with just this matrix on it. So I've got some room to write. Here's my matrix. And what I'm going to do is I'm going to go ahead and start out by saying that the determinant of this matrix is some number x. I don't know what x is, but I want to go ahead and set a variable for that determinant because as I row reduce, the determinant is going to change. And now I have a variable, I can use that variable to record the changes. So the first thing I might do is get rid of this 1. I'm going to take row 3 minus row 1. And so that gives me 1, 1, 3, 4, 2, 0, 0, 2, 3, 5. 1 minus 1 is 0. 5 minus 1 is 4. 6 minus 3 is 3. 8 minus 4 is 4. And 5 minus 2 is 3. All right, what happened to the determinant? Well, the row that was being changed was row 3, and the coefficient of row 3 is a 1, and so there is no change yet to the determinant. And so the determinant is still x. So we're going to keep going. If I look at my leading entries, they're out of order. So I'm going to take these two rows and switch them. I'm going to switch row 2 and row 3 now. So I'll have 1, 1, 3, 4, 2, 0, 4, 3, 4, 3, 0, 0, 2, 3, 5, 0, 0, 0, 3, 4, and 0, 0, 3, 6, 1. What happens when we change the order of the two rows? We switch two rows. That changes the determinant by a factor of -1. It flips the sign of the determinant. And so now the determinant isn't x anymore, it is now -x. All right. My leading entries are starting to look pretty good until I get to the bottom row and I want to get rid of that 3. And I'd have to use a 2 to cancel that 3. So I need a linear combination of 6. Let's see. So I'm going to take 2 times row 5 minus 3 times row 3. So let's see what we get now. 0, 4, 3, 4, 3, 0, 0, 2, 3, 5, 0, 0, 0, 3, 4. All right, 6 minus 6 is 0. 12 minus 9 is 3. And 2 minus 15 is negative 13. Let's check that again. 2 times row 5 is 2. 3 times row 3 is 15. 2 minus 15 is negative 13. All right. Well, now what happened to the determinant? We were altering row 5, and the coefficient of row 5 was a 2, and so the determinant just doubled from negative x to negative 2x. Well, we have one more step. We have to eliminate the 3 in the bottom row. So I'm going to take row 5 minus row 4. And that's going to give me 1, 1, 3, 4, 2, 0, 4, 3, 4, 3, 0, 0, 2, 3, 5, 0, 0, 0, 3, 4, and 0, 0, 0, 0, and then negative 13 minus 4 is negative 17. And now what happened to that determinant? I was altering row 5, and the coefficient of row 5 is a 1, and so there's no change. My answer is still 2x. But now my matrix is in echelon form. And so we can find this determinant by multiplying 1 times 4 times 2 times 3 times negative 17. And let's see, how much is that? That is, oh, that's going to be a big number. 4 times 2 is 8. 8 times 3 is 24. 24 times 17 is, let's see, 28. It's 168, and 24 is 408, and there's a negative sign here, so negative 408. We're not done yet, though, because that is an x. That equals negative 2x. And so we have negative 408 equals negative 2x. And so if we divide both sides by negative 2, then we get x is equal to positive 204. And that's the determinant of the original matrix, not the one that we ended up with. So, all right, so this took us, a few minutes now to work through this, but this was the determinant of a 5 by 5. And we did this by doing some row reduction, tracking what happened to x. At the end, x got multiplied by negative 2, and so we had to divide by negative 2 to get back to our original answer. Anyway, this wraps it up for today. So you take care, and we'll see you next time.